So we're going to talk a lot about air sealing today, and the obvious reason for air sealing is to keep energy in, but the one that's not discussed as much is the health and durability issue. This diagram right here out of the Builder's Guide to Cold Climates, show this diagram a lot. It shows, we're talking about vapor barriers and air leakage, vapor diffusion. Everyone always pays attention to vapor barrier details a lot and doesn't pay attention to air leakage. This diagram shows that the air leakage is way more important. So this is a 4x8 sheet of sheetrock. Shows that in an entire heating season with an interior temperature of 70 and 40% relative humidity, that 1/3 of a quart of water will diffuse through that sheet of sheetrock. Drywall is extremely vapor open. Vapor will diffuse through drywall very easily. So you can see that only 1/3 of a quart is going to go through a 4x8 sheet. The same conditions, interior temperature is 70, 40% relative humidity, 1 square inch hole, 30 quarts of water. This is why we hammer on air sealing details, because the potential for building durability problems, rotting walls, mold. I mean, we see it all the time. We see attics that are just full of mold and rotting out. We see wall assemblies that are rotting from moisture intrusion through air leakage. Damaged insulation. You just saw one a couple weeks ago where the insulation was just soaking wet. And you'll see, we'll show some photos here later, but this is why we feel like it's very important to address the air leakage issue.
That diagram comes from this book, The Builder's Guide to Cold Climates. And once again, we very highly recommend this book.
So what causes air leakage on a building is a couple of items. The stack effect, which is try to look at a building like a hot air balloon. A building is under a positive upward pressure. When the interior conditions are warmer than outside, the building actually has uplift on it. There's actually pushing on the upper reaches of the building. You can see here it's pushing up and out on the upper reaches of the building, and on the lower levels there's a negative pressure created, and that's where the air usually infiltrates, comes up and exfiltrates on the upper end of and the roof and wall systems on the upper side of the building.
If you ever see a building under construction, like a 3 or 4 story building that's been wrapped for construction purposes, you look at that plastic, it'll be pushing out at the top and sucking in at the bottom, and that's exactly what's going on here.
I actually saw it this morning on the new Missoula Federal on Brooks.
And somewhere in the middle, not necessarily at the floor plane, but somewhere around the middle of the building is a neutral pressure plane. And below that, air is sucking in through air leaks, and above that, air is going out through air leaks. But either way, it's costing the owner money in the wintertime, because sucking cold air in at the bottom and letting hot air out at the top.
Wind also has a huge effect on the air leakage of the building. We had a project once where a customer had a fully spray foamed house, and they're like, my energy bills are crazy high. So we did a blower door test, and the blower door test result was that the building was really pretty airtight. It was at 2 air changes per hour, which is the volume of air, the entire volume of air in the building leaked out 2 times in 1 hour with the blower door fan running. That's a pretty tight building in our opinion, but this particular house was up on a hillside outside of Great Falls, and the wind blows there all year round. And so the simulated 20-mile-an-hour wind that we were putting on it with the blower door, that happens all year round for them. So they were getting 2 air changes per hour.
All the time.
All the time. It's like they had a blower door running the whole time. So yeah, that's why, even though they had a fully foamed house, they still had comfort and energy issues. The other thing that's not a diagram that's not in here that really affects air infiltration and durability issues, as well as indoor air quality, is large exhausting appliances, whether that's the 500 CFM range hood, or it's a B-vented water heater, or it's a fireplace, an open burning fireplace. Those are all exhausting appliances that pull air and heat out of the building and air leaks in from other areas.
So yeah, a concept to keep in mind is that for every CFM that goes out of the building, one comes in somewhere. So especially in the wintertime, if you're running that 500 CFM range hood fan that we see from time to time, they're sucking in 500 CFM of freezing cold air somewhere else in the building, and they're having to heat that.
So we get into a few thermal images here of different, pretty much all these thermal images are just from actual jobs. Some of them are new construction, some of them are existing. I would say probably at least half of them are built within the last 10 years.
5 to 10 years.
5 to 10 years.
And these are the most typical things that we see all the time, places that buildings leak air. We'll be going over a lot more air leakage details when we get into the code stuff as well, so we'll just be flying through these right now.
So this is a thermal image of an attic access, unsealed, not very well insulated, air just leaking in around the perimeter of it.
With an infrared camera, when you see these streaks across the surfaces, that's air leakage.
And yeah, the camera shows temperature differential. So in some situations, the air leaking in is going to be warmer than the air in the building, and in some situations, the air is going to be colder. So we're going to be seeing some different temperatures. Right here, the temperature gradient, the orange is warmer, the blue is the coldest. We're going to see some where it's the opposite because we did the thermal image in the summer versus the winter. So this one, the attic was cold and we had air leaking in around the perimeter. Here's a detail of a good attic access, a sealed hatch, where there's a foam board that goes over the top of the drywall, or ideally plywood first so that it can be adhered to it, and then a gasket that goes around the perimeter of the attic access as well.
We'll be going over that.
We'll go over that in more detail, yeah. Recessed can lights are a huge area for air leakage. Using airtight cans helps with that. We recommend building a foam box over them because even the airtight cans aren't airtight. Windows and doors are another area that we see a lot of air leakage. This is air leaking up between the door frame and the framing. That's not the actual door leaking.
Right, they didn't foam properly around the door when they put it in, and so behind the trim that air is leaking straight up the wall behind the trim.